Hello, and welcome back to my YouTube channel. My name is Professor Govala, and today I'm going to be talking to you about symmetry properties in orthogonal functions. And essentially, the main reason why I want to talk about this is because this video leads into two very crucial examples I want to do after this. And essentially, it's important for us to understand these symmetric properties in order to easily solve the following videos to come. So again, this is just simply part one of what's going to be a three-part series. And what I'm going to do here now is I'm going to break down proof number one into two-part series, 1a and 1b. And the first part being 1a says that an even times an odd function is going to equal an odd function. So call this 1a. And the second part of 1 is saying that the integral of an odd function over a time period t is going to be 0, call this 1b. And then for proof number 2, the first part, call it 2a, is that an even times an even is equals to an odd times an odd, which is going to be equals to an even function, call this 2a. And then the second part of 2 is saying that the integral of an even function over a time period t is not equated to 0. So then 1a says that an even times an odd is equals to an odd. So let g of t equals x of t times y of t, where x of t is an even function. So that means that x of minus t is equated to x of t. That's the definition of an even function. And y of t is an odd function, which means that y of negative t is equals to minus y of t. So then in order to prove that g of t, which is an even times an odd function, is equated to an odd function, we need to prove that g of minus t is equated to minus g of t. So then we can continue and then say that g of minus t is equals to x of minus t times y of minus t. But we know that x of minus t, since it's an even function, is just x of t. And we know that y of minus t, since it's an odd function, is minus y of t. So then we get, then this is minus x of t times y of t, which is then equated to minus g of t, right? Because this here is essentially g of t and there's a minus in front of it. So then we can just say minus g of t. Now again, since minus g of t is equals to g of minus t, we say then that we can conclude that an even times an odd function is equated to an odd function. So then this is our proof. So to be more formal, we can say that an arbitrary period real function that is even times an arbitrary period real function that is odd is equated to an arbitrary period real function that is odd. And in terms of a mnemonic or a way to memorize this, we can say then that an even, which is a plus, and if we're given an odd, which is a minus, we can say that plus, which is an even, times a minus is equated to a minus, which again is an odd. So again, this is simple multiplication. We know that a positive times a negative is a negative. So I hope this makes sense. Again, I'm trying to talk about it slowly so that everybody understands. But if you have any questions, please leave them down in the comment section below and I'll be sure to get back to you. So the second part of proof 1, call it 1b, says that we need to prove that an integral over a period t of an odd function gt dt is equals to 0, again, given that g of t is odd. So what I'm going to write here is that the period t is going to go from minus t over 2 to t over 2 times my odd function gt dt. I can rearrange this to be minus t over 2 to 0 gt dt plus the integral from 0 to t over 2, my odd function gt dt. So what I want to do now is I want to label a term. So let an arbitrary term u be equals to minus t. So du is equals to minus dt, or a change in u is equals to a negative change in time. So then we can say then that when t is equals to minus t over 2, u will be t over 2. And when t is equals to 0, u will also be equals to 0. So then we can go ahead and rewrite this function here. So we can say then that this is going to be t over 2, because again, at t is negative t over 2, u is t over 2. So the 0. Now we change the terms. So this is g to the minus u times minus du plus the integral of 0 to t over 2 gt dt. So now we can notice that since this is an odd function, I can bring out the negative, and this negative sign here changes my terms. It flips my parameters. So I can rewrite this as 0 to t over 2 minus g of u, because it's an odd function, du plus integral of 0 to t over 2 gt dt. Now this is very important. Since u and t are simply dummy variables, these two integrals are identical but opposite in signs. So then my integral of negative t over 2 to t over 2 gt dt is equated to this integral of 0 to t over 2 gt dt. I'm writing this one first, minus integral of 0 to t over 2 gu du, which again is just 0, simply because these two are identical. I hope that makes sense. If you have any questions or comments, please leave them down in the comment section below, and I'll be sure to get back to you. So then the next part of this video is to prove part 2, which we're going to start with what's called 2a. And essentially, it's proving that an even function times an even function is equals to an odd function times an odd function, which is equals to simply an even function. So what I'm going to say is that let f of t equals to x of t times y of t, where in this case, let x of t be even. So that means that x of minus t is equals to x of t, and y of t, let it also be even, where again, y of minus t is equals to y of t. So then to prove that f of t, which is an even times an even function, we need to prove that f of minus t is equals to f of t. So let's go ahead and do that. So f of minus t is equals to x of minus t times y of minus t, which is simply equated to x of t times y of t. And this here is simply just f of t. So that means that f of t is equals to f of minus t. So then this proves that an even times an even function is equated to an even function. So the next part is to say then that let h of t be equals to m of t times n of t, where m of t is an odd function. So that means that m of minus t is equals to minus m of t, and n of t is also an odd function. So that means that n of minus t is equals to minus n of t. So then to prove that h of t, which is an odd times odd function, is an even function, we need to prove that h of minus t is equals to h of t. Okay, so h of minus t is m of minus t times n of minus t, which is equals to minus m of t times minus n of t. This minus cancels out with this minus, so then we're left with just m of t times n of t, which is just h of t. So then we've proven then that h of minus t is equals to h of t. So then this is an even function as well, completing our proof. So then to be formal with a definition, we can say then that an arbitrary periodic real function that is even times an arbitrary periodic real function that is even, or an arbitrary periodic real function that is odd times an arbitrary periodic real function that is odd, is always equals to an arbitrary periodic real function that is even. And again, mnemonically, you could think about it as a plus times a plus, or an even times an even, will always equals to an odd times an odd, which is always going to be equals to an even function, or a plus. So the last part of number 2's proof is 2b, which says that an integral in time times f of t dt does not equate to 0 if f of t is even. All right, so let's go ahead and do the same thing we did in 1b and say then that we take the integral from minus t over 2 to t over 2 of f of t dt. This is simply minus t over 2 to 0 f of t dt plus 0 to t over 2 f of t dt. Let's go ahead and let u equate to minus t, so that du is equals to minus dt. So then by this parameter change, we can say that if little t is equals to minus t over 2, then u is equals to just positive t over 2. And when t is equals to 0, then u is equals to also 0. So then let's go ahead and plug in u into this first term. And we can say then that positive t over 2 to 0 f of minus u times minus du plus the integral from 0 to t over 2 f of t dt. So now what we can notice is two things, that this function here is an even function, so it can just equate to f of u, and this negative here will flip my parameters. So I can rewrite this as from 0 to t over 2 f of u times du, and then plus the integral from 0 to t over 2 f of t times dt. And similar to 1b, since u and t are simply dummy variables, the two integrals are identical with the same signs. So then, therefore, we can write it clean and say that the integral from minus t over 2 to t over 2 of this even function, f of t dt, is the same thing as saying the integral from 0 to t over 2 f of t dt plus the integral from 0 to t over 2 f of t dt, since u and t are simply dummy variables and are identical. So then this is just equals to 2 integral from 0 to t over 2 f of t dt, which is clearly not equals to 0. And that is the end of our second proof. So again, we'll be using these proofs heavily in the upcoming videos. If you like the video, please give it a thumbs up and please share the video to your colleagues and friends. If you like what the YouTube channel is providing, please consider subscribing. It really helps the algorithm. Thank you.